We have basically discovered a lot of these trade-offs, or at least we have made you aware of those trade-offs. I wanted to spend a few minutes and show you how do we really make this RF transceiver a little differently than what I had given you as the ideal, but not very practical RF transceiver. So here's how a typical system will work. And it's not by any means that everything fits in one of these boxes no matter what. But if you ask somebody to draw a car for me, they will probably draw something that has maybe 4 wheels. And so this is what basically the analogy here, right? So everything starts from an analog source most of the times. And this analog source may actually be voice. It may be sensor data. It may be something that you're simply trying to detect. Usually, immediately, you're going to go through an analog to digital conversion. So you basically digitize. There will be some ideas of introducing source coding to improve the transmission of those bits. For example, error correction codes may actually be included here. Then there will be some type of a modulation based on what we discussed before. Finally, we're going to convert this to our RF frequency, depending on what the system might be. You're going to go through the PA, you're going to transmit through the duplexer or a switch, and off you go. The waves are in the air. And exactly the opposite will happen when you're basically trying to receive a signal. The antenna will hopefully get something from the intended reception. It will guide it now to the receiving path. There's going to be an LNA, or low noise amplifier, whose main job is to take this tiny signal and make it slightly more detectable, so it will amplify it. It will at some point down convert it directly to baseband or through intermediate bands. It depends on the system architecture. And then you're going to basically follow the previous route. You're basically going to digitize, you're going to demodulate all the way back to producing the signal that you want, for example, voice in a system. So that's a very typical diagram. That's a very typical way of handling information in an RF system. But I want to very quickly hint on the most important decisions that an RF engineer has to make in real life. And I won't be able to cover all of them today, but here's a few interesting key points. First of all, you have to worry about amplification. We already said some major things about it. You have to worry about the efficiency of your amplifier in the transmit path, but you also have to worry about its linearity. As I mentioned before, you can't simply pollute the spectrum just because you can't make a linear amplifier. Similarly, amplification is very critical in the receive path. This guy here, unfortunately, in addition to amplifying the signal, it also adds noise. Too bad. Not only you're starting with a very weak signal, but at the same time, you're now adding noise. And so that's why this L-N stands here, low noise amplifier. So it's very critical to make sure this noise is as small as possible. And so we make a lot of sacrifices in this design just to keep the noise low. We have to worry about linearity, and I already mentioned that before. And linearity is actually true throughout the system here. For example, your PA has to be linear, but your filter has to be linear too. It doesn't make sense to worry too much about the PA being linear when the filter actually will destroy everything. Similarly, this guy here, the LNA, must be linear as well. Otherwise, the signal you're trying to receive is not going to look the same at its output than it was at its input. You have to worry about sensitivity and dynamic range. I mentioned a few things about this before. Sensitivity means what's the lowest signal you can receive. We've been talking about negative 100 dBm as an example in GSM, but you have to decide what's my lowest signal and what do I do if something is below that. Dynamic range is actually equally important because in addition to this negative 100 dBm signal, somebody may have right next to you perhaps a 60 dBm signal blocker, and now you have to work in the presence of that signal blocker. So how do you basically handle this intentional or unintentional signal blocker is very, very critical. Now, other things that come into real-life applications is form factor. You may come up with the best receiver in the world or the best transmitter in the world, but it still has to fit inside the phone. And those phones are not very forgiving. Most people in this world think that the only thing you need on a phone is a screen, a battery, and the good app. Oh yeah, the fact that this thing has to also transmit. Oh come on, this is default, right? It just works. Somehow it magically will get your phone. There is no room to put an antenna or a receiver or anything in there. You have to worry about cost, right? So this system has to, every 2 or 3 years, you have to improve the performance and lower the cost at the same time. Some people call this misfortune. I call it job security. So it's a very, very important factor as well. Also, if you come up with a good design, you better find somebody who's willing to manufacture that and to manufacture it at scale. And just manufacturing becomes such a big deal. If you don't believe me on that, just look at what happened with, and I'm not going to mention companies here, but just look at what happened with some companies who failed in manufacturing safe batteries. Having phones explode is not the best thing in the world, right? And lastly, adaptivity is a key issue as well. I just mentioned before that the next generation of systems is very likely they will have some autonomy. And what I mean by adaptivity here, I don't mean that you as a user tell the system, okay, move from this band to the next band because the next band is quieter. I mean that the system itself makes that decision. It learns and it adapts. So those systems we have today are not there yet. But the fields are merging. RF field is merging with machine learning, with AI, and you will see in the future our kids won't really have the same phones that we do. So again, this is more of a conclusion to kind of bring a lot of the concepts together and make you aware that if there is nothing else that you can remember from this class, I mean after the final exam, is that there are trade-offs. And so trade-offs is the key that you will actually face in industry.